Hello, thank you for being interested in my talk. So in this presentation, I will talk about dampings in wave equations and other hyperbolic partial differential equations. I'm going to also relate the concept of damping to negative feedback in infinite dimensional systems theory. So throughout the talk, we are interested in the properties of this abstract Cauchy problem, which is an abstract differential equation on an infinite dimensional Hilbert space. And our semigroup generator has a very specific form. It consists of an operator A, which generates a contraction semigroup, often a unitary group, and it represents somehow the undamped dynamics of the equation. And then the second term, the minus BB star, captures the effect of the damping in the system. And throughout the talk, we are interested in finding conditions on the operators A and B, which guarantee the stability of the equation. And by stability, I mean that we would like that all of the solutions corresponding to all different initial conditions of the equation converge to zero in norm as t goes to infinity. And we are also very interested in investigating the rates of this convergence. And I'm going to begin by some introduction and illustrative examples of the types of equations we can consider. My main results concern sufficient conditions for stability of our equation. And finally, in the last part of the talk, I'm also going to speak about similar types of models, but this time with nonlinear dampings. And the point of this presentation is to illustrate somehow the connections between some concepts. And for this purpose, I'm going to make some oversimplification and hide some assumptions, but I'm of course happy to describe these in greater detail later if you ask me. Our prime motivation comes from study of wave equations, and these are prime examples of the types of models we're interested in. So if we consider a two-dimensional domain, then our wave equation can be defined in such a way that W at point xi and at time t describes the deflection of the wave profile. And here the double dot is the second order time derivative. We have the Laplacian, which is a second order spatial derivative. And in this velocity term, causes the damping in our equation. And damping is parametrized by this damping function d, which is a function with non-negative values. And these types of equations have been are known as wave equations with viscous damping. And the stability properties of this equation are understood relatively well already. And in particular, it's known that the size of the so-called damping region contributes to the type of stability we get. And damping region is simply defined as the subdomain where the damping function has non-zero values. Whenever this damping region has positive volume, we get asymptotic stability, but the rates of convergence depend on the properties of and geometry of this region. And in particular, it's possible to either get exponential stability or weaker forms of stability like polynomial stability. And these two cases are distinguished by the so-called geometric control condition, which tests whether all of the rays which reflect optically within the spatial domain either meet the damping region eventually or alternatively fail to do so. And if this condition holds, then all of these rays will meet the damping region, like in the case on the left here. And then we get exponential stability, which is very, very strong type of stability. On the other hand, if we can have these kinds of rays which bounce back and forth and never meet the damping region, we get a weaker form of stability. And the wave equation indeed fits in our framework, and it can be expressed in as an infinite dimensional abstract Cauchy problem with a generator of the form A minus BB star. If you haven't seen this before, then don't worry. The main message is simply that this equation is within our framework. And if you have seen this before, then A, the operator within undamped dynamics, is the wave operator without any damping. And then on the other hand, the operator B includes the damping parameter function as a multiplication operator. And indeed, A is a skew adjoint operator, and B here is a bounded operator. In addition to this viscous damping, it's also possible to consider boundary dampings. So in this case, we don't have any velocity term in our equation, the PDE, but instead it's included in a boundary condition. So these types of dampings can be technically demanding from many points of view, but in this situation as well, somehow the damping region where the D has non-zero values contributes to the type of stability we get. And again, in many cases, the distinction between exponential stability and weaker forms of stability can be made based on these kinds of geometric control conditions. And finally, I can give you another very practical example dealing with my car. And with vehicles made out of sheet metal, when we drive, the parts of the car that especially contain flat surfaces, like the exteriors of the doors, can tend to vibrate and maybe resonate with the movement of the car. And this, on the other hand, translates to noise in the interior of the car, and this can be unpleasant. And we can actually improve the sound isolation and acoustics of the vehicle by increasing the damping in these parts of the car. We can do this by adding some damping materials, especially on these flat surfaces. And this damping material is quite clever. It consists of a relatively thick, very sticky rubber, and on top of this, thin aluminum layer. And this rubber sticks very closely to the sheet metal so that it attaches very firmly. And on the other hand, the aluminum foil makes the damping patch relatively stiff, which then causes like a resistance to vibrations. This is just meant as a very illustrative example. I won't go into details how this is formulated as an infinite dimensional abstract Cauchy problem. This is left as an exercise. But indeed, we are interested in the stability of this equation, but before investigating the behavior of solutions, we would like to know if this equation has solutions in the first place. In the case where B is a bounded operator, we have well-known perturbation theory for contraction semigroups, which guarantees that also the operator A minus BB star does generate a contraction semigroup, and because of this, our equation has well-defined solutions for all initial states. On the other hand, in the case of boundary dampings, the operator B fails to be bounded because somehow it maps outside our state space X. And in this case, the semigroup property of A minus BB star is more challenging. But one way we can consider this is using infinite dimensional systems theory. And in this approach, we replace our original equation with a linear system where we have our operator A, which is a generator of contraction semigroup, but instead of the damping term, we equip our system with an input acting through B, which is taken from our damping operator. And similarly, we equip the system with an output, which is defined by the adjoint B star of B. So this gives us an infinite dimensional linear system. And then what we can observe is that if we take our output Y, multiply it with a minus sign, and then feed it back to our input U, then we formally get a new system where this generator or the main operator is exactly of the form A minus BB star in our original equation. In linear systems theory, this is known as negative output feedback. And because of this connection to our original equation, we can observe that we can use feedback theory in investigating the existence of solutions of our equation, because if we can find a feedback result which guarantees the semigroup property of the system under this negative feedback, then this is exactly what we wanted to know. Indeed, there is a lot of this kind of theory in infinite dimensional systems theory, even in the case of unbounded operators B and boundary dampings. And it turns out that under very, very mild assumptions on the original operators A and B, the resulting system obtained from feedback is so-called well-posed system, and in particular A minus BB star generates a contraction semigroup. So this answers the question of existence of solutions, so we can move on to the investigation of stability. And one way to do this, now that we know that A minus BB star generates a contraction semigroup, is to investigate the behavior of the resolvent operator of A minus BB star on the imaginary axis. And the classical result of Gerhardt, Greiner, Pruss states that if the resolvent operator of A minus BB star exists and is uniformly bounded on the imaginary axis, then our equation is actually exponentially stable, and therefore all solutions of the equation decay to zero as t goes to infinity, and this happens at a uniform exponential rate. As we saw in the case of our damped wave equation, we don't always get exponential stability, but also weaker forms of stability can be investigated using the resolvent operator. And a result by Borichev and Tomilov in particular states that if the resolvent exists and grows at most polynomially along the imaginary axis, then we in fact get asymptotic stability for our equation, and in addition we get a rational decay rate of convergence, not for all initial conditions, but all initial conditions which correspond to classical solutions of our equation. And in addition, there is a direct correspondence between the polynomial growth bound of the resolvent and the decay rate of the classical solutions as t goes to infinity. We are interested in stability, and it turns out that feedback structure that we observed for our equation is also useful in this context. And in particular, it can be roughly stated that we get stability for our equation with A minus BB star precisely if this open loop system that we investigated has the so-called property of observability. And observability is a system theoretic property which measures how easy it is to reconstruct the unknown state X from this kind of a linear system, now without any inputs. And this reconstruction should be done based on only observing the output of this system over some time interval. And since observability measures how much information this B star output carries of our state, we can view this property in a way which kind of tells us how well this B star can see, especially the unstable modes of the operator A. And this is the way that observability also leads to being a property which tells us how well our damping term can affect and damp these unstable modes of A. And the way we can investigate stability is through the resolvent estimates. And what we would do for a concrete PDE, we would identify the abstract representation of our equation and then go on to estimate the resolvent operator. And there are several direct techniques for this, like multiplier methods or very powerful microlocal analysis. And after we get these resolvent estimates, we get stability results and decay rates. When we would be using observability estimates, the process would be slightly different. So we'd start with the abstract equation, and then we would check if A and B satisfy some kind of an observability estimate or the original open loop system. Then we would like to use results which, based on this observability estimate that we have derived, gives us a resolvent estimate for A minus BB star. And again, this would imply stability and a decay rate. And this is the way that in this way, observability estimates are a kind of a method of simplifying the process and splitting it into more but simpler parts. And the simplicity comes from the fact that the observability estimates are verified for the undamped problem, which doesn't contain the damping term, and in this way it is simpler. And this is a very classical approach, especially in the case of exponential stability, but also for weaker forms of stability, like polynomial stability. This has been used in several instances, especially for wave equations. And I can now present my first main results, which consist of these kinds of results which, based on an observability condition, guarantees a resolvent estimate for the damped equation. And in the first result, we consider a condition which is an observability type condition, which looks like this. So this is a parametrized set of inequalities where the functions m and small m are non-decreasing and positive valued functions. And we would like to check that for some functions m and m, this condition holds for all values of the frequency parameter s, and for all elements x in the domain of A. And if this condition holds, then we can consider that our operators A and B satisfy this kind of an observability condition. And our main result then is that under this precise condition, we have a resolvent estimate for the operator A minus BB star on the imaginary axis. And this resolvent estimate involves both of these functions m and capital M from the observability estimate, as well as an additional term which grows polynomially. And this eta parameter should be chosen in such a way that this condition holds. And if you know systems theory, you can identify this as the so-called transfer function of our linear system. And the purpose here of the parameter eta is somehow roughly to measure the level of unboundedness of our operator B. And especially in the case where B is a bounded operator, eta is just taken to be 0. And then also in the case of many unbounded operators B, we can still use eta equals 0 in this case. But for instance, in the case of wave equations, we know that eta cannot be 0, but instead we have to have a positive value. But in all cases that we can consider, eta is always at most 4. And this resolvent estimate, using the results we saw before, immediately also gives us the stability of our original equation and also a decay rate, especially in the case where the parameter functions m grow at most polynomially. We get a rational decay rate for all classical solutions of our equation. And this result was presented in our paper from 2 years ago. And this is just one sample of the results we presented. And in addition, in this paper, we investigated several other different observability type conditions, some of them which are applicable, especially in the case of where A is a skew joint operator, and some of them applicable for abstract second order systems, especially for the wave equations, as well as for some time domain type conditions. And in each of these cases, we showed that the observability type condition in question implies a resolvent bound for the operator A minus BB star, and therefore also the stability and decay rate for our original equation. And let's look at how our result can be applied in the setting of the wave equation with boundary damping. So again, we return to the situation of our wave equation with a condition which has a damping parameter in the boundary condition. And we're especially interested in the case where we don't have exponential stability, so we can have these bouncing rays which never meet the damping regions. And the motivation here is that in these cases, the rates of convergence of solutions have not been investigated very actively in the literature. And our plan is to identify and verify an observability condition that is satisfied by the corresponding operators of the abstract model. And in addition, we would like to find this parameter eta in such a way that we get this bound which also appears in our result. And like I mentioned before, for eta equals 0, this is not satisfied in the case of our particular model, and therefore we are looking for an eta which is strictly positive. And this question was investigated in detail by Nicola in our group, and in his recent work he especially found very nice and good estimates for the value of eta. And he showed especially that the value of eta depends heavily on the shape and geometry of the spatial domain of the wave equation, as well as on the properties of its boundary. And he showed, for instance, that if the spatial domain is a rectangle, then we can take eta to be anything greater than 1. And in the case where the domain has a smooth boundary, then we can take particular values which depend on the other properties of the boundary. For instance, in the cases where it's flat or concave, we can improve these estimates. But in all of these cases, we can observe that the values of eta that we should use are greatly improved from the baseline estimate of eta equals 4 that we already saw. So we can always improve by something like 75%. And it turns out that the observability condition that we would need is something that we can directly find from the literature. And because of this, we can combine this information directly with our estimate of the eta parameter to arrive at a stability result for the boundary damped wave equation. And our result says that we get stability and a rational decay rate of the classical solutions of our equation with an alpha parameter which can be taken to be anything greater than 3. And this is in fact a new result for the wave equation on the rectangle, because the only previous result we are aware of only considers the case where the rectangle is damped on a one single full edge. And in this case, it's possible to use Fourier decomposition to express the resolvent operator and estimate it accurately. But this is no longer the case for us when the damping is somewhere else besides on a single line. And the way that we get the decay rate is that the observability condition contributes to this quadratic term in the resolvent growth, and using the parameter value for eta in the case of the rectangle gives us a resolvent growth with 3 plus epsilon. I can conjecture that the optimal decay rate in this case is most likely equal to 2, so our decay rate is probably not optimal. This comes down to a relatively fundamental limitation in the kinds of results that we present. And in particular, in our results, we decouple this observability estimate from this measure eta of unboundedness of the operator B. Because of this decoupling, our results have to somehow account and prepare for the worst type of unboundedness and weakest type of observability separately, whereas in many PDE cases, these could somehow beneficially counteract and partially cancel each other out. But nevertheless, we can see that we can get relatively easily to relatively accurate and near optimal decay rates, even in the case of multidimensional equations. Especially in the case of one-dimensional equations, we often get optimal decay rates with our approach. Okay, and now I'll move on to the last part of my talk, where I want to consider, again, damped equations, but this time the damping contains nonlinearity. So we again have these operators A and B, but now we also have this function phi. And we assume that this phi is a continuous and monotone function. And this monotonicity is important from the point of view of the damping. So monotonicity requires that we somehow, this function phi preserves directions. And this way we can guarantee that somehow the direction of the damping does counteract the dynamics of the undamped model. And the monotonicity is typical, for instance, for the so-called saturation function, which is linear between two points and then maxes out afterwards. But this is also true for other functions with some directionality properties. And again, we start by asking whether our equation has solutions. And in the case where B is a bounded operator and phi is locally Lipschitz, this is relatively easy to answer. And our equation has solutions which are now determined by a nonlinear semigroup of contractions. But on the other hand, in the case of boundary dampings where B is an unbounded operator, this is a much more challenging problem. There's a lot of results on this, but indeed this is much more technical. The results I'm citing here focus on these kinds of abstract models, but then in addition there's a lot of work on individual PDEs, for instance, with boundary damping. But we can again benefit from the approach of systems theory and feedback. And in this situation, we can start by looking at a system, again with the main operator A, and with an input, but this time we include the function phi in our input. So this makes this a nonlinear system. But nevertheless, if we again take our output y, multiply it with -1, and feed it back into our input u, we get a system which has exactly the same form as our original equation. And because of this, we can again benefit from feedback theory in investigating well-posedness and stability of our equation. But this time it has to be somehow nonlinear feedback theory. And my first main result concerns the existence of solutions. And simply put, under mild additional assumptions, on top of phi being a continuous and monotone function, our equation does have well-defined generalized solutions for all initial states. And in addition, the system is contractive in the sense that two solutions may come closer to each other over time, but they may never diverge. The full version of our result also guarantees existence of classical solutions for suitable initial data, and it's also valid for so-called impedance-passive well-posed systems and system nodes. And finally, we also have a separate result with slightly stronger assumptions on phi, which allow us to also include an external input in our system, acting through the nonlinearity phi. But now that we have investigated the well-posedness, we can turn to the question of stability of our equation. And in this case, we have to make additional assumptions on phi. For instance, phi obviously cannot be the zero function, otherwise we don't necessarily get any stability because of lack of damping. But we make this kind of a result which gives a lower bound for the values of phi near the origin. And the main purpose of this assumption is to just guarantee that while we approach the origin, the function phi doesn't vanish too quickly, but it should vanish at most linearly. But after this, outside the neighborhood of the origin, we don't need a very strong lower bound on the function phi. But assuming this condition, our result says that if the corresponding linear model is strongly asymptotically stable, then also our nonlinear system is globally asymptotically stable, And all of the solutions of this equation converge to zero as t goes to infinity. We can now apply our well-posedness and stability results for a Timoshenko beam model. So here we have a one-dimensional beam model where W is the displacement profile of the beam along its length, and theta is the rotation angle of the length. And the beam dynamics are described by the first line, and on the second line we have the boundary conditions which describe the beam being clamped at one end. And on the other end we have boundary conditions which are nonlinear. And if we remove these nonlinear saturation functions phi, then this would be a standard type of boundary damping for the Timoshenko beam. But now indeed the damping has some saturation limits. But our results say that because we know the equation without saturation is in fact exponentially stable, we also get well-posedness and global asymptotic stability for the nonlinear damped model. And in particular, the beam system has well-defined generalized solutions for suitable initial data, and then our solutions converge in norm to zero as t goes to infinity. And this brings me to the end of my talk, where I presented a systems theoretic and feedback theoretic viewpoint on the existence of solutions and stability of damped abstract Cauchy problems. And I've also presented some new results on well-posedness and stability for models with nonlinear damping. So thank you very much for listening.